concept of a sequence along with its notation. So a sequence is just a function from the natural numbers to some field. So we have that the co-range of my function is just a set of natural numbers. Sometimes we write a set of whole numbers. But the notation we use is actually not a functional notation. So suppose that we have the following sequence: 1, 3, 5, 2, 24. A whole bunch of numbers. Let A denote that sequence. Rather than writing it as like f evaluated 1 is 1, f evaluated 2 is 3, etc. We write these as subscripts. So I'll say that A sub 1 is 1, A sub 2 is 3, A sub 5 is 5, A sub 4 is 2, A sub 5 is 24. So let's say the fourth term in my sequence is 2. So the subscript tells you the term in the sequence. The sequence 1, 3, 5, 2, 24 is a finite sequence. It just has a finite number of terms in that sequence. 2, 4, 6, 8, ... is an infinite sequence. These 3 dots are called ellipses. So these are my ellipses here. And this just means keep continuing with the same pattern. 1, 1, 2, 3, 5, 8, 13 is a special sequence. We call it the Fibonacci sequence. So some sequences are named because people use them a lot. And so we call this sequence the Fibonacci sequence. Okay, partial sums. Suppose that A sub n is a sequence. Then the sequence S sub n is called the sequence of partial sums derived from the sequence A sub n if S sub 1 is A1, the first term in this sequence. S sub n plus 1 is plus A sub n plus 1 for all natural numbers n. Series. A series is a sequence of partial sums. So when we talk about a series, we're just talking about a sequence of partial sums. And so let A sub n be the following sequence: 1, 3, 7. Let's determine a series from this sequence. Let's determine the sequence of partial sums. And usually we actually call this guy, the last one, the series. So we usually say that the series is 1 plus 3 plus 7. Okay, so S sub 1 is A1, meaning S sub 1 is just 1. S sub 2 is S1 plus A2. Let A sub n be the sequence 1, 3, 7. Let's derive from this a series. So S sub 1, the first partial sum, is A1. So S1 is equal to 1. S2 is equal to S1 plus A sub 2. And so S1, which is 1, plus A2, which is 3. And the partial sum S3 is just the partial sum S2, which we found was 1 plus 3, plus the last term, A sub 3 in the sequence, 7. And so my sequence of partial sums is just 1, 1 plus 3, 4, 1 plus 3 plus 7, 11. We usually call this last term my series. One plus 3 plus 7. So usually we denote this last term in my sequence of partial sums and call that the series derived from the sequence 1, 3, 7. Okay. We'll usually use some notation to simplify what I've written here. And so the summation notation, this symbol here is called the summation symbol. It is sigma. It's the capital Greek letter sigma. It denotes the sum. So if you've ever looked in Excel, you'll notice that they have this symbol here. And when you click on it, it just adds whatever quantity you're highlighting. And so a sub 1 plus a sub 2 plus a sub 3 plus dot 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 a sub n, the series, can be represented in a more compact notation as the sum. So this is the summation symbol, sigma, j, the what we call the dummy index, equaling 1, the lower limit, to n, the upper limit. So of a sub j. So this symbol here means that I add, so you notice I'm adding, each of these a sub j's for j equaling 1 up to n. So I replace j here by the lower limit, 1, plus a sub, well, I go in the next natural number larger than this lower index, 2, plus dot, 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 and the very last subscript that I'm going to be using, a sub, whatever the upper limit is, in this case, we call it n. And so this can be written more compactly in this notation. Now, we can actually start out not at a lower limit of 1, but maybe a lower limit k sub 0 for some integer k sub 0. So the sum, k equaling k sub 0 to n of a sub k, is a sub k sub 0 plus a sub k sub 0 plus 1 plus dot, 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 a sub n. Here, of course, I'm assuming that k0 is less than or equal to n. If k0 is greater than n, then this will just be a series with no terms. It would just be 0. It'll be the empty series. Okay, so let's do an example. Suppose I have the sum j equaling 1 to O, and j equaling 1 to 3 of j plus 1 squared. Well, let's replace j by 1, so it's 1 plus 1 squared, by 2, 2 plus 1 squared, by 3, 3 plus 1 squared. So you notice that this series here does not actually involve j. So j is just this index that we created just so that we could write this notation. So this j was only part of the sigma notation. It's really not part of the actual series. So that's why we call it a dummy index. It's just something created so that it would help us in the notation. Let's do an example. Let a equaling 2, 4, 8, 3 be a sequence. Then we can construct the following series from this sequence. And so we get the sequence of partial sums. Maybe I should just say that. So this is a sequence of partial sums. And it's just 2, and then we add 2 plus 4, 2 plus 4 plus 8, 2 plus 4 plus 8 plus 3, from which we derive the series 2 plus 4 plus 8 plus 3. So I just add 2 plus 4 plus 8 plus 3. It's the last of these partial sums in the sequence of partial sums. In other words, the series 2 plus 4 plus 8 plus 3 can be written as the sum from k equaling 1 to 4, because, well, there are 4 terms. And I just call each of the terms a sub k. So let me give you some properties of series. So let a sub n and b sub n be series, be sequences, and let c be a member of some field, usually say the real numbers or something. And each of these sequences here, each of the members are in the same field, let's say. Then we have the following. Oh, that was kind of a horrible notation if I'm going to be using n's. So let's use k's. I use n as the upper limit, so let's use k as my dummy index. Okay, so the sum, k equaling 1 to n, of just adding up c is c times n. If you add up 1 plus 1 plus 1, you get, add 1 plus 1 plus 1 n times, you get n. The sum k equaling 1 to n of c times a sub k is just c times the sum k equaling 1 to n of a sub k. The sum k equaling 1 to n of a sub k plus b sub k is the sum k equaling 1 to n of a sub k plus the sum k equaling 1 to n of b sub k. So here with the distributive property, you can always distribute out a constant in front of a if you're constant, if you have a common constant in a sum of a whole bunch of terms, you can factor it out by the distributive property. You have, well, using the commutative associative property, you have that the series of a sum of two sequences is just the sum of their series derived from these sequences. The sum k equaling 1 to j a sub k plus the sum k equaling j plus 1 to n of a sub k is the sum k equaling 1 to n of a sub k. The sum k equaling 1 to n of 1 is n. The sum k equaling 1 to n of k is n times n plus 1 over 2. The sum k equaling 1 to n of k squared is n plus 1, 2n plus 1 over 6. The sum k equaling 1 to n of k cubed is n squared over n plus 1 squared over 4. You could keep going on with higher and higher powers of k, but I just ended at 3. Have to end somewhere. Okay, so, and you'll get things that, formulas that are similar. Okay. You notice that Polynomial, this is a polynomial in k of degree 0. You get a polynomial in n of degree 1, polynomial in k of, and so this is a polynomial in k of degree 1. You get a polynomial in n of degree 2, k of degree 2, n of degree 3, k of degree 3, n of degree 4. And you'll, in general, that's what you'll get, something of that type. And the coefficients are relative, well, can be derived in a algorithmic way. And it turns out that there's actually a function that can tell you what these coefficients are. Okay, so let me actually show you that these properties for series are true. And so the first one, the sum k equaling 1 to n of c equaling c times n. So let's do the initial case. Let's suppose n is equal to 1. So the sum of one of my c's is just c. Therefore, and of course, c times 1 is c. So the sum j equaling 1 to n of my c's is just c times n when n is 1. Let's do the induction case. Suppose the sum for j equaling 1 to k of c is c times k. Then let's determine what happens when I replace k by k plus 1. So the sum j equaling 1 to k plus 1 of c is equal to the sum j equaling 1 to k of c plus, well, the last term, which is just c. But this, by the induction hypothesis, is just c times k. I can factor out a c, and I just get c times k plus 1. But now, if I look here, this is the same formula if I replace k here by k plus 1. Therefore, I've shown that the induction case is true, that the induction hypothesis implies that the next term is also true. So therefore, by the principle of mathematical induction, we have that the sum j equal 1 to n of c is equal to c times n. For all n, natural numbers n, with c being some number, let's say in some arbitrary field. So I'm done with that proof. Let's show that I can factor out. This is the same as CA1 plus CA2 plus CA3 plus dot 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 CAN. And it just says I can factor out the C's. So this is just a distributive property, saying I can factor out. If C is in common everywhere, I can factor it out. Okay, so let's show this. So let's do this by induction. So let's first show that if I replace n by 1, this is still a true statement. So let's replace n by 1. And so I get the sum k equaling 1 to 1 of c a sub k is just, well, there's only one term in this sum. It's just c a sub 1. And let's look at this guy. So c times the quantity, the sum k equaling 1 to 1 of a sub k, well, that's just going to be a sub 1. So this is CA1. These are equal. Therefore, these two are equal. And so I've shown that these are the same when n is equal to 1. So I've shown the initial case. Let's do the induction case. Suppose that this is true for capital N. So suppose for k equaling 1 to capital N, c sub a sub k is equal to c times the quantity sum k equaling 1 to capital N a sub k. Let's look what happens at the next term. So let's do the sum k equaling 1 to n plus 1 of c times a sub k. Well, it's going to be the sum of the first n terms plus the last term. So the sum k equaling 1 to n of c a sub k plus the last term, c times a sub n plus 1. But by assumption, I have that this is equal to this term, c times the quantity sum k equaling 1 to n of a sub k. Now I look and I see that these terms have the same common factor, c. So this is c times the sum k equaling 1 to n, a sub k plus a sub n plus 1. But this is the same as the sum k equaling 1 to n plus 1 a sub k. This is just the first n terms, sum of the first n terms, and then added to it the last term. But that says that if I assume that this is true for n, then replacing n by n plus 1, it's also true. And so I've shown the induction case. And so therefore, by the principle of mathematical induction, I have that the sum k equaling 1 to n times c a sub k is equal to c times the sum k equaling 1 to n of a sub k for every natural number n. And that's what I wanted to prove. Next. The sum. So the series of a sum is the sum of these series. And so let's show that. So let's replace n here by 1. And so the sum k equaling 1 to 1 of a sub k plus bk is just a1 plus b1. Let's look at this when n is 1. So this is sum k equaling 1 to 1 of a sub k plus the sum k equaling 1 to 1 of b sub k. Well, this is just a1 and this is just b1. And so a1 plus b1 is the same. Therefore, these are the same when n is equal to 1. So I've shown the initial case. Let's do the induction case. And so let's suppose that this statement was true for capital N. So let's suppose that the sum k equaling 1 to n, a sub k plus bk is equal to sum k equaling 1 to n of ak plus the sum k equaling 1 to n of bk. Let's look at what happens when I go to the n plus first case. So the sum k equaling 1 to n plus 1 of a sub k plus bk is equal to, well, the sum of the first n terms, the sum k equaling 1 to n of a sub k plus bk plus the last term, a sub n plus 1 plus b sub n plus 1. By the induction hypothesis, I have that this first term is equal to the sum k equaling 1 to n of ak plus the sum k equaling 1 to n of b sub k. But now I can regroup these. And so this is the sum of k equaling 1 to n of a sub k plus a sub n plus 1, which is just the same as the sum k equaling 1 to n plus 1 of a sub k. Plus, well, I can group the sum k equaling 1 to n of bk with b sub n plus 1. But the sum k equaling 1 to n of b sub k plus b sub n plus 1, this is just the last term in this series, the sum of k equaling 1 to n plus 1 of b sub k. And so I've shown that the induction hypothesis holds. Therefore, by the principle of mathematical induction, the sum k equaling 1 to n of ak plus bk is the same as the sum k equaling 1 to n of ak plus the sum k equaling 1 to n of bk for all natural numbers n. So I'm done with that. Let's look at the next one. The sum k equal 1 to j of a sub k plus the sum k equaling j plus 1 to n of b sub k of a sub k is equal to the sum k equaling 1 to n of a sub k. So the initial case, let's let j equal 1. So this is sum k equaling 1 to 1 of a sub k plus the sum k equaling 2 to n of a sub k. But that's just a1 plus k equaling 2 to, actually I probably should have said j plus 1 here, 1 plus 1, which is 2 to n of a sub k. But this is just the same as, well, this is the first term of the series, and so it's the sum k equaling 1 to n of a sub k. And I don't really have to show that. Well, I did, but I didn't really have to show it. But and the sum k equaling 1 to n of a sub k is a1 plus the sum k equaling 2 to n of a sub k. So this is the same as the sum k equaling 1 to 1 a sub k plus the sum k equaling 1 plus 1 to n of a sub k. So we've shown that the sum k equaling 1 to j a sub k plus the sum k equaling j plus 1 to n a sub k is equal to the sum k equaling 1 to n of a sub k when j is equal to 1. So let's do the induction case. Oh, I want to keep it as a j. It doesn't really matter. The sum k equaling 1 to j of a sub k. Assume the sum k equaling 1 to j a sub k plus the sum k equaling j plus 1 to a sub n to n of a sub k is equal to the sum k equaling 1 to n of a sub k. Then the sum k equaling 1 to n of a sub k is the same as the sum k equaling 1 to j of a sub k plus the sum k equaling j plus 1 to n of a sub k by the induction hypothesis. But this is the same as, well, for this term, this is just a sub j plus 1 plus the sum k equaling j plus 1 to n of a sub k. But this is just the sum k equaling 1 to j plus 1 of ak plus this last term, the sum k equaling j plus 2 to n of a sub k, which means that we've shown the induction hypothesis, the induction step works. And so therefore, by the principle of mathematical induction, we have that the sum k equaling 1 to j of a sub k plus the sum k equaling j plus 1 to n of a sub k is equal to sum k equaling 1 to n of a sub k. Property 5, the sum k equaling 1 to n of 1 is equal to n. Let's do this by induction. And so, well, the sum of k equaling 1 to 1 of 1 is just 1, only one term there. And, well, when n is 1, n is 1. And so, therefore, the sum k equaling 1 to n of 1 is equal to n when n is 1. Let's do induction. And so the induction case is assume that k equaling 1 to capital N of 1 is equal to n. Then I want to show that this works for the n when I replace n by n plus 1. So let's do the sum k equaling 1 to n plus 1 of 1. That's the same as the sum k equaling 1 to n of 1 plus 1, just writing out the last term. But this, by assumption, is n. So this is equal to n plus 1. But now this is the same as the induction hypothesis when I replace n by n plus 1. So therefore, I've shown the induction case works. So by the principle of mathematical, so therefore, by the principle of mathematical induction, the sum k equaling 1 to n of 1 is just equal to n for every natural number n. And that's what I wanted to show. Next. I'm going to do a construction. So this will be a a way to actually construct and a technique that will actually determine the answer. So rather than prove it, we're going to actually prove it by construction, basically. And so the sum k equaling 1 to n of k squared minus k minus 1 squared is equal to, well, let's use the special product formula, the perfect square trinomial formula. So this is k squared minus 2k plus 1. Now let's multiply the negative inside the parentheses. So I'll change all these signs. So I get minus k squared plus 2k minus 1. The k squares cancel. So you just get the sum of 2k minus 1. Now, using the above properties, I have that this is the same as the sum of 2k plus the sum of 1, negative 1. I can bring the 2 out in front, the negative 1 out in front. So this is 2 times the sum k equaling 1 to n of k minus the sum k equaling 1 to n of 1. But I know what property number 6. Sum k equaling 1 to n of k is equal to n times n plus 1 over 2. So let's try to prove this, not using induction, but trying to derive it using previous sums that we have already proven. So the sum k equal 1 to n of k squared minus the quantity k minus 1 squared is equal to, well, let's use a special product formula to expand k minus 1 squared. This perfect square trinomial. It's equal to k squared minus 2k plus 1. The k squares cancel. And distributing the minus sign inside the parentheses, I get that this becomes a minus k squared, this becomes a plus 2k, and this becomes a minus 1. So now, canceling out the k's, squares, I have that this is equal to the sum k equaling 1 to n of 2k minus 1. So now, this is the same as the sum k equaling 1 to n of 2k plus the sum k equaling 1 to n of negative 1. I can, just using the fact that the sum is additive, and I can take the scalar out in front of the summation. And so using the fact that, again, the sum is linear, I get that this is equal to 2 times the sum k equal 1 to n of k minus the sum k equal 1 to n of 1. I know that the sum k equaling 1 to n of 1 is just n. And so I have determined that the sum k equaling 1 to n of k squared minus k minus 1 quantity squared is just 2 sum k equaling 1 to n of k minus n. Now let me try to rederive this in another way. And so, let me call this computation that I've just done equation 1. so I can refer back to it. So let's just expand this. So when k is equal to 1, this is just equal to 1 squared minus, well, 1 minus 1 is 0 squared. When k equals 2, this is equal to 2 squared minus 1 squared. When k is equal to 3, 3 squared minus 2 squared, k is equal to 4, 4 squared minus 3 squared, etc. When k is equal to n minus 2, n minus 2 squared minus n minus 3 squared. When n is equal to n minus, when k is equal to n minus 1, n minus 1 squared minus n minus 2 quantity squared. And lastly, when k is equal to n squared minus n minus 1 quantity squared. Well, the 1 squares cancel, 2 squares cancel, 3 squares cancel, the 4 squares will cancel, the n minus 2 squares cancel, the n minus 1 squares cancel, n minus 3 squares cancel with the previous. So all I have left, and when this happens, we call this a telescoping series. And so basically everything cancels except for the first and last terms. And so I get that this is equal to n squared minus 0 squared, which is just n squared. But I've shown that both of these are equal to, well, first, 2 sum k equal 1 to n of k minus n, and it's equal to n squared. So let's set these equal and try to solve for the sum k equal 1 to n of k. And that's what we want to determine. So let's add n to both sides of my equation, draw out the n, divide by 2. And so I have that the sum k equal 1 to n of k is just equal to n times the quantity n plus 1 all over 2. And that's what I wanted to show. Let's show that the sum k equal 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 all over 6. We'll do that using mathematical induction. Because in the very last one, I didn't use mathematical induction, so let's use mathematical induction. So first, I want to show that this is true when n is equal to 1. Well, the sum k equal 1 to n, k equal 1 to n when n is equal to 1 of k squared is just going to be, well, the sum of 1 squared, which is just 1. Plugging in n equal 1 into this formula here, I get 1 times 1 plus 1 times 2, well, n plus 1, 2n plus 1 all over 6. When n is equal to 1, well, 2 plus 1 is 3, 1 plus 1 is 2, 1 is just 1. And so I have 6 divided by 6, which is 1, which is the same thing that I got for the other sum, the left-hand side. And so the right-hand side and left-hand side are both equal to 1 when n equals 1. So I've shown that this formula is true when n equals 1. Let's suppose that this formula is true when little n is equal to capital N. I then want to show that this formula works, is true, when I replace capital N by capital N plus 1. And so, if the sum k equal 1 to n of k squared is n plus 1, 2n plus 1 over 6, then the sum k equal 1 to n plus 1 of k squared is going to be, well, the sum of the first n terms of this plus the last term. And so replacing k here by n plus 1, I get an n plus 1 squared. And well, I've written out the first n of these, k equal 1 to n of k squared. Now, by the induction hypothesis, I have that the sum k equal 1 to n of k squared is just n plus 1 times n plus 2n plus 1 all over 6, plus this last term. Well, to add these, I'm going to have to find a common denominator, which is 6. So let's multiply and divide this last term by 6. So first, I have the common denominator 6. I have n plus 1, which is in common. So let me factor that out. Then I have an n times 2n plus 1. Let's multiply the n inside the parentheses. So I get n times 2n is 2n squared. N times 1 is just n. Factoring out the n plus 1, I just have 6 times n plus 1. So let's multiply the 6 inside the parentheses. So we get a 6n plus 6. Combining like terms, n plus 6n is 7n. Now let's factor. So I can factor 2n squared plus 7n plus 6 as n times 2n gives me my 2n squared. 2 times 3 gives me my 6. 2 times 2n is 4n, plus 3n gives me my 7n. Lastly, let me rewrite n plus 2 as n plus 1 plus 1, 2n plus 3 as 2n plus 2 plus 1. Factoring out the 2, I get 2 times the quantity n plus 1 plus 1. So now I see that if I replaced this n by n plus 1, I get the same formula. Therefore, assuming that the formula is true when little n is equal to big N, I've shown that this implies that the formula is true when I replace little n by capital N plus 1. Therefore, the induction hypothesis, the induction case holds. Since both the initial and induction cases hold, then I've shown that by mathematical induction that the sum k equaling 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 over 6 for every natural number n. Let's do property 8. I want to show that the sum k equaling 1 to n of k cubed is n squared times n plus 1 quantity squared over 4. Let me derive it like what I did with the previous example. So I'm going to use the knowledge of the sum of from k equaling 1 to n of 1 is n. The sum k equaling 1 to n of k is n times n plus 1 all over 2. And the sum k equaling 1 to n of k squared is n plus 1, 2n plus 1 over 6 to show this. So let's do that. So just like previously, let's look at the following sum. The sum k equaling 1 to n of k to the 4th minus k minus 1 to the 4th. So all I do is I give this sum where this power here is 1 more than the power that's given here. And so k minus 1 to the 4th is just k to the 4th minus 4k cubed plus 6k squared minus 4k plus 1. Let me change all the signs inside the parentheses. So this becomes a minus k to the 4th, so these cancel. Plus 4k cubed minus 6k squared plus 4k, no, I'm sorry, plus 4k minus 1. Let's use the linearity of the sum to simplify this. So I'll bring the 4 outside the summation, the negative 6 outside the summation, the 4 outside the summation, and the negative 1 outside the summation. We're trying to determine the sum k equaling 1 to n of k cubed. I know the sum k equaling 1 to n of k squared is n plus 1, 2n plus 1 over 6. The sum k equaling 1 to n of k is n plus 1 over 2. The sum k equal 1 to n of 1 is just n. Now let's simplify this. The 6's cancel. Let's multiply the n inside the parentheses. So I get n squared times plus n. Let's cancel out the 4's. So, well, 4 divided by 2 is 2. So let's multiply the 2n inside the parentheses. So I get 2n squared plus 2n. And then lastly, your n. Let's multiply these two terms together. So I get a 2n cubed, and it's a minus here. I get n squared plus 2n squared is 3n squared. I change the sign, so it's minus 3n squared. And then plus n, change the sign, so it's a minus n. Plus your 2n squared, canceling out. 2n minus n is just n. The n's cancel. 3n squared, well, 2n squared minus 3n squared is minus n squared. Let me call that formula or equation 1. Now, let's use the fact that this is a telescoping series. So everything cancels except for the last term, the n to the 4th, and the first term, the minus 0 to the 4th. So this, just like in the previous case, is just equal to n to the 4th. So therefore, since these are the same, this must equal n to the 4th. So I have 4 sum k equal 1 to n of k cubed minus 2n cubed minus n squared is just equal to n to the 4th. Let's bring these two terms to the other side. So it's n to the 4th plus 2n cubed plus n squared. Factor out n squared. What remains is a perfect square trinomial. So this is just n plus 1 quantity squared. Divide both sides of my equation by 4. So I get the sum, k equal 1 to n of k cubed is equal to n squared, n plus 1 squared all over 4. And that's what I wanted to show. So let's do some examples. On page 738, find the next term in each sequence. So basically determine the pattern and continue on with the pattern. So I have here that this is 1, 8, 27. So you take 1 cubed, 2 cubed, 3 cubed, 4 cubed. Or maybe I should just write it this way. 1 cubed. 2 cubed. 3 cubed. 4 cubed. 5 cubed, etc. So the next term in my sequence is 125. And that's your answer. Let me do problem number 18. AR squared, AR cubed. And so I keep multiplying by R. And so this is going to be AR to the 4th will be the next term. 30. Assume that each sequence is defined recursively. Find the first 4 terms of each sequence, okay? And so we've defined this recursively. So I have, well, A1 is -5. To find A2, I'm just going to have to subtract I'll just have to take the negative of A1 and subtract 3. And so A2 is equal to 5 minus 3. And so I have that A2 is equal to 2. A3 is minus A2 minus 3. And so it's a negative 2 minus 3, negative 5. And A4 is minus A3 minus 3. And so A4 is equal to a 5, which is equal to 2. So I see the following pattern. We have, this is negative 5, 2, negative 5, 2, etc. And those are the first 4 terms of this sequence. Determine whether each series is an alternating infinite series. Well, certainly it's an infinite series. Because it doesn't stop. So these indicate that, and there's nothing afterwards, indicate that it's an infinite series. Next, it alternates because the sign alternates. So it alternates. Well, it's an alternating series. Because we see it's a minus 1 plus 2 minus 3, etc. And then it says minus 1 to the n. So for the even ones, for the even n, it'll be positive. For odd n, it'll be negative. And so it keeps alternating between signs. So it keeps changing between plus and minus. Therefore, it's both an alternating series and an infinite series. So this is an alternating infinite series. Okay. 42. Evaluate each sum. Okay. So it's the sum, k equaling 3 to 3k. So I first replace k by 3, 4, 5, 6. Now I stop because it says to start when k is 3, but I want to stop when k is 6. So I keep replacing each of these k's by the natural numbers, starting at 3, ending at 6. And once I calculate each of those, I add them up. And so this is equal to 9 plus 12 plus 15 plus 18. So that's 30, and 24 is 54. And so the sum of these numbers, these 4 numbers, is 54. Let's do an example. just using some facts that we know. So evaluate the sum of 1,000 of 5j plus 3. So obviously this idea of just adding up, plugging in numbers, adding them up is not going to be very efficient if I have to do this 1,000 times. So let's use the fact that I know that the sum k equaling 1 to n of k is equal to okay, is equal to, this is a little slow, there it is equal to n plus 1 over 2, and the fact that the sum k equaling 1, well, maybe I'll just sort of say that. Okay, so now I can evaluate this. So the sum j equaling 1 to 1,000 of 5j plus 3, this is equal to 5, using the fact that the summation is linear. This is the same as the sum, j equaling 1 to 1,000 of bringing out the 5 out in front, j, plus the sum j equaling 1 to 1,000 of 3. So this is equal to 5. The sum j equaling 1 to 1,000 of j, well, just use the fact that the sum up to n is n times n plus 1 all over 2. And the sum, j equal 1 to 1,000 of 3, well, you're just adding 3 plus 3 plus 3 1,000 times. And so that's just 3 times 1,000, 3,000. So this is equal to well, hmm. 1,000 divided by 2 is 500 times 5 is 2,500. 1,000 plus 1 is 1,001. And 3 times 1,000 is 3,000. And so I get that this is equal to 2,505,500. And that's what the sum of these is equal to. The Fibonacci sequence. So let u sub n equal 1 plus radical 5 to the power n minus the quantity 1 minus rad 5 to the power n all over to the n times rad 5. Let this define the nth term of a sequence. Show that u sub 1 is equal to 1, u sub 2 is equal to 1, B, show that u sub n plus 2 is equal to u sub n plus u sub n. Draw the conclusion that u sub n is a Fibonacci sequence. So first off, let's recall that u sub n being a Fibonacci sequence, so u sub n is a Fibonacci sequence if u sub 1 is equal to 1, u sub 2 is equal to 1, and u sub n plus 2 is equal to u sub n plus 1 plus u sub n. Basically, it's what we're going to show in parts A and B. Okay, so let me do part A. So u sub 1, let me look at u sub 1. So u sub 1 is equal to, maybe I'll do, well, let's just plug in n equal 1 here. So I get 1 plus rad 5 to the power 1 minus 1 minus rad 5 to the power 1 over 2 to the power 1 rad 5. So this is equal to 1 plus rad 5 minus 1, and let's see, I'm just multiplying the negative 1 inside the parentheses, plus rad 5 all over 2 rad 5. The 1s will cancel. And so I get this is equal to 2 rad 5 over 2 rad 5. So this is equal to 1. Good. I've shown the first part. Next, I want to look at u sub 2. So u sub 2 is equal to 1 plus rad 5 squared minus 1 minus rad 5 squared all over 2 squared rad 5. So this is equal to, let's square this out. So by the special product formula, this is just 1 plus 2 rad 5 plus rad 5 squared, which is 5. Minus, let's square this out. And so by the special product formula, this is a perfect square trinomial. This is 1 minus 2 rad 5 plus 5 all over 4 rad 5. And so let's get rid of the parentheses. Let's change all the signs. So this is 1 plus 2 rad 5 plus 5 minus 1 plus 2 rad 5 minus 5 over 4 rad 5. 1, 5 cancel. So this is equal to 4 rad 5 over 4 rad 5 5. And so this is equal to 1. Good. So I've shown that both U1 and U2 is equal to B. So let's look at U sub n plus 2. This is equal to 1 plus rad 5 to the power n plus 2 minus 1 minus rad 5 to the n plus 2 over 2 to the power n plus 2 rad 5. So this is equal to 1 plus rad 5 to the n, 1 plus rad 5 squared, 1 minus rad 5 to the n, 1 minus rad 5 squared, all over 2 to the power n plus 2 rad 5. So this is equal to 1 plus rad 5 to the n, 1 plus 2 rad 5 plus 5. Again, because it's perfect square trinomial, using the special product formulas. 1 minus rad 5 to the n. Again, using the fact that this is a perfect square trinomial. This is 1 minus 2 rad 5 plus 5, all over 2 to the n plus 2 rad 5. And so I have 1 plus rad 5 to the n. This is just 1 plus 5 is 6. 2 rad 5 minus 1 minus rad 5 to the n. 1 plus 5 again is 6 minus 2 rad 5. All over 2 to the n plus 2 rad 5. I can divide everything by 2. So I can divide the numerator and denominator here by 2. And so this is 1 plus rad 5 n. And so 6 divided by 2 is 3. The 2's cancel, so rad 5 minus 1 minus rad 5. The n. 6 divided by 2 is 3. The 2's cancel, all over 2n plus 1 rad 5. Since I'm dividing by 2, one of the 2's cancel. So let me write this as 1 plus rad 5 to the n. One plus rad 5 plus 2. So I can write 3 as 1 plus 2. And 1 minus rad 5 to the n 1 minus rad 5. 1 minus rad 5 plus 2. Again, I can write 3 as 1 plus 2 all over to the n plus 1 rad 5. And so this is equal to, well, I can multiply, I can just distribute the 1 plus rad 5 to the n inside. And so I get 1 plus rad 5, the n plus 1 plus 2, 1 plus rad 5 to the n minus, let's do the same thing here. So it's a 1 minus rad 5 to the n plus 1. I'm multiplying the negative of this to the n. I get a negative 2. 1 minus rad 5 to the n. Over 2 n plus 1 rad 5. And so this is equal to let's take these first and third terms. So it's a 1 plus rad 5 to the n plus 1 minus 1 minus rad 5 the n plus 1 over to the n plus 1 rad 5 plus this term, which is 2. Let's factor out the 2. 1 plus rad 5 to the n minus 1 minus rad 5 to the n all over 2 to the n plus 1 rad 5. So this is equal to 1 plus rad 5 n plus 1 minus 1 minus rad 5 n plus 1 2n plus 1 rad 5 plus the 2's cancel, so we get 1 plus rad 5 the n minus 1 minus rad 5 n over, again, one of the 2's cancel, so 2 to the n rad 5. This is u n plus 1. This is un. And so I've shown that this satisfies u sub n plus 2 n plus 1 plus u sub n. So C. Since un, u1 is 1, u2 is 1, un plus 2 is equal to un plus 1 plus un. So this was in part A, we showed this, and this was in part B. Then this sequence is a Fibonacci sequence. And so I'm done. Maybe I'll just say done. Note the following. Let's derive the formula. So now how is this formula derived? Okay, so first let me have the following lemma. So suppose x squared is equal to x plus 1. Then I have that x sub n plus 1 is equal to x times f n plus 1 plus fn for all natural numbers n, where this is my Fibonacci sequence. So I want to show that anytime I have that x satisfies the equation, x squared equals x plus 1, I must have that x to the power n plus 1 must equal x to the n, it must equal x times f sub n plus 1 plus f sub n for the Fibonacci sequence. So let's prove that. And let's prove this using induction. So let's first look at the initial case. So let's show that this is true when n is equal to 1. So x sub 1 plus 1 is just equal to x sub 1. So I'm going to suppose that, oops, well, I know that so this is x squared, okay? And now let's look at, so I know that this, that, you know, now let's look at this guy, see if this holds. And so I have x f sub 1 plus 1 plus f sub 1. Let's see what that's equal to. Well, f sub 2, 1 plus 1 is 2. I know f sub 2 is just 1. And it, oops, that was a typo. I know f sub 1 is 1 because it's a Fibonacci sequence. So this is equal to x plus 1. But we assume that x squared is equal to x plus 1. So this is x squared. And so I have that this is equal to x squared. This is equal to x squared. Therefore, I've shown that x to the n plus 1 is equal to x f sub n plus 1 plus f sub n when n is equal to 1. Now, and so that proves the initial case. Let's show the induction case. And so let's suppose that x to the power n plus 1 is equal to x f sub n plus 1 plus f sub n. So let's suppose that this induction hypothesis is true. Then let's look at x to the power n plus 2. Well, maybe I'll say it this way. Okay. X to the power n plus 1 plus 1. So this is equal to x to the power n plus 2, or let's say x times x to the power n plus 1 just by properties of exponents. So this is equal to x times, well, by the induction hypothesis, we assume that x to the power n plus 1 is just x times f sub n plus 1 plus f sub n. So this is equal to x squared f sub n plus 1 plus x times f sub n, just multiplying the x inside the parentheses. But x squared is equal to x times x, is just equal to x plus 1. So this is equal to x f sub n plus 1 plus f n plus 1 plus x f sub n, just multiplying the f sub n plus 1 inside the parentheses. And so this is equal to x times, well, I can group the first and last terms together, f sub n plus 1 plus f sub n plus the last term. But due to the fact that this is a Fibonacci sequence, I have that this sum here is just equal to f sub n plus 1 plus 1. And so I've shown that this formula is true when I replace n by n plus 1. Therefore, by the principle of mathematical induction, so by the principle of mathematical induction, we have that x to the power n plus 1 is equal to x f sub n plus 1 plus f sub n for every x, for every n. And that's what I wanted to show. Okay, so now let's show the following. Okay, so good enough. Well, that the Fibonacci sequence is just going to equal the nth term of the Fibonacci sequence will just equal 1 plus rad 5 to the n minus 1 minus rad 5 to the n over 2 to the n rad 5. Okay. Where, again, the sequence is the Fibonacci sequence. Okay, so let's show that. So first, let's look for what the solutions of that previous equation looked like. And so let's try to solve the quadratic equation, x squared equaling x plus 1. And we're going to be using, I guess, the quadratic formula to show that. Okay? So, x squared equals x plus 1. Oh, come on. And so, there it is. So this is just x squared minus x minus 1 equaling 0. And so let's use the quadratic formula that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So x is equal to 1 plus or minus the square root of 1 plus 4 over 2. So x is equal to 1 plus or minus rad 5 over 2. Okay, so by the lemma, x squared equaling x plus 1 implies that x to the n plus 1 is equal to x f sub n plus 1 plus f sub n. Let me define f sub 0 as equaling 0, just to make my life easier. Then, if I do that, then I can plug in n equals 0, and this will make sense. So if I plug in n equals 0, then that would be a 0. This would be f sub 1, which is just 1. And this would just be x to the power 1. And so then this would still make sense, even when n were equal to 0. So I could replace minus 1 for any natural number n, and this will still be true. And so x to the n is equal to x f sub n plus f sub n minus 1. Okay, so, well, we know that x is equal to this. And so, here, let me put the plus minus a little higher. And so I have that 1 over 2, the n is equal to 1 plus rad 5 over 2 f sub n plus f sub n minus 1. Since I know that this is one of my solutions, and so I have that 1 plus rad 5 over to the n over, oh, come on, 1 plus rad 5 to the n over to the n is equal to 1/2 f sub n plus rad 5 over 2 f sub n plus f sub n minus 1. Let me call this equation 1. Similarly, since I know that it's true for both plus and minus, then let me plug in the 1 minus rad 5 over 2. So let's plug in that solution. So I also have 1 minus rad 5 over 2 to the n is equal to 1 minus rad 5 over 2 f sub n plus f sub n minus 1. I guess I'll say, and we have this. So I have that, let's see, this is really slow, that I have 1 minus rad 5 to the n over 2 to the n is equal to 1/2 f sub n minus rad 5 over 2 f sub n plus f sub n minus 1. So let's call that 2. Okay, so now let's just look at 1 minus 2. So let's look at equation 1. Subtract from that equation 2. And so I have, I guess I'll need more room there. 1 minus rad, no, that's a plus. 1 plus rad 5 to the n over 2 to the n is equal to 1/2 f plus rad 5 over 2 f sub n plus f sub n minus 1, and then a minus 1 minus rad 5, the n over 2. So there'll be a minus 1/2 f sub n. There'll be a minus. No, minus and minus become a plus. Rad 5 over 2 f sub n minus f sub n1. So let's subtract these. Almost everything will cancel. And so I get 1 plus rad 5. Okay, I get 1 minus rad 5. Okay, come on. 1 minus, come on. 1 minus rad 5 to the n over 2 to the n minus 1 minus rad 5 to the n over 2, to the n, common denominator, so I could put them all over the same common denominator. The 1/2 f sub n's cancel, the f sub n minus 1's cancel, and so I just get rad 5 f sub n. And so let's write this as f sub n is equal to, well, 1 minus rad 5 to the n, writing these all over the same common denominator, minus, oh, wait, there was a typo. The first one was a plus, because this guy had a plus there. Minus 1 minus rad 5 to the n all over 2 to the n. But I also had to divide by a rad 5 to solve for this. So rad 5. And that's what you wanted to show. Pity I couldn't do it all in one line. Okay, so this is equal to there. So I've basically shown that indeed the Fibonacci sequence can be written as that formula. So it's sort of amazing that you can write 1, 1, 2, 3, 5, 8, what was it, 13, 21, etc., using this formula. So each term can be calculated with this simple formula. Simple closed formula. So it's called the closed formula. So the nth term in your sequence is just equal to this above formula. Okay, so that finishes